When an aeroplane moves forward, the air begins to flow over its wings. Once it's moving fast enough, this airflow over the wings lifts it off the ground. In flight, the airflow over the wings continues to support the aeroplane and keeps it up in the air, provided it's moving forward fast enough. This is how it happens. As the airflow passes over the wing's curved upper surface, it speeds up temporarily and slows down again at the rear. This speeding up causes a reduction in air pressure on the wing's upper surface, and this gives the aircraft its lift. But when aircraft fly faster than about 400 miles an hour, things begin to get complicated. The speed at which sound travels through air comes into the story. This film will describe some of these complications and show why aircraft intended to fly at speeds near or above that of sound have to be designed differently from low-speed aircraft. Let's first consider how sound travels. Slowing down the picture shows how the sound is produced. The vibrating prongs give the air a succession of pushes, and like pressure waves along a spring, the sound waves travel on through the air. Sound waves are, in fact, one kind of pressure wave. Like ripples on a pond, they spread out from their source in all directions. Not all pressure waves are audible, but all small disturbances, audible or not, travel outward at the speed of sound. Watch this explosion. A mile away. Its sound takes 5 seconds to reach us. At sea level, sound travels at about 760 miles an hour. But the speed depends on the temperature of the air, which drops as we climb upward. In the stratosphere, which begins at about 36,000 feet, the speed of sound is only about 660 miles an hour because of the lower temperature. Now look at the wing again. Every point on it, by traveling through the air, sets up tiny disturbances which move outwards as pressure waves at the speed of sound. And parts of these disturbances reach the air ahead of the wing. Here, smoke is used to show how the air flows. Lowering a flap affects the airflow well ahead of the wing. This is because the tiny pressure waves warn the air ahead of the wing's approach. This warning allows the air to part smoothly around an aircraft, provided it's flying well below the speed of sound. At higher speeds, approaching the speed of sound, the exact relation between the speed of the aircraft and the speed of sound becomes very important. It is called the Mach number, usually shortened to M. This is how it is calculated. This aircraft has flown 6/10 of a mile. In the time the sound wave traveled 10/10 of a mile. It has flown at 6/10 of the speed of sound in the same atmospheric conditions. That is, it has flown at Mach 0.6. This aircraft is flying at Mach 0.9. At high speeds, it's essential for the pilot to know his Mach number, and Mach meters are fitted to all high-speed aircraft. What actually happens to the air and the aircraft when approaching the speed of sound? The airflow speeds up as it passes over the wing and reaches its maximum speed at a certain point on the wing. So the Mach number of the air at this point is greater than that of the aircraft as a whole. As the aircraft's speed increases, so does the local Mach number at this point on the wing. Eventually, just at this point on the wing, the air reaches the speed of sound, although the aircraft, as a whole, is still flying slower than sound. The aircraft's Mach number, when this happens, is called its critical Mach number, usually written m-crit. Soon after this, things can begin to happen. This aircraft is buffeting violently. Aircraft vary in their behavior above the critical Mach number, but until designers overcame them, there were always some ill effects. They're caused by shock waves. Let's see what this means. If a model wing is put into a high-speed wind tunnel, a special photographic technique known as schlieren makes visible the places where the pressure of the air changes as it passes round the wing. In this picture, wherever the color is green, the speed and pressure of the air are almost constant. Blue has been chosen to show up the areas where pressure is falling fastest, while red shows where the air is being slowed down and pressure is increasing. Now look at a diagram. At the critical Mach number, the airflow is moving across the wing at this point at exactly the speed of sound. M equals 1. Above the critical Mach number, the point grows into an area in which the flow is faster than sound. M is greater than 1. Everywhere else, the flow is slower than sound. M is less than 1. The rear boundary of this area is formed by a shock wave. As the speed is increased still further, the shock wave grows larger. What causes the shock wave? Think again of the tiny pressure waves radiating out at the speed of sound from every point on the wing. The ones coming from points on the rear part of the wing, such as this one, meet airflow coming the opposite way and make less and less headway until they can't travel any further forward at all, because the airflow itself is moving backwards as fast as they are moving forwards at the speed of sound. It's like trying to step off an escalator going the wrong way. The little pressure waves pile up, building into one big pressure wave, the shock wave. And here's the real thing in the wind tunnel. The wing has just passed its critical Mach number, and there's the shock wave, red, because it's a sudden, sharp increase in pressure. But shock waves don't only form on wings. Wherever the air speeds up enough in its passage over the aircraft, on cockpit, canopy, fuselage and tailplane, there too, shock waves will form. The most striking effect of shock waves is a sudden, very sharp increase in the aircraft's drag. This is because the shock wave heats up the air and compresses it. And this absorbs a lot of extra energy, which has to be continuously supplied by the engines. The rate at which the drag increases is itself highest somewhere around Mach 1, although the actual drag goes on growing all the time. This sudden increase in drag above the critical Mach number is what used to be meant by the sound barrier. Most of the other ill effects of shock waves arise because they cause the airflow to separate from the wing's surface. This produces a large wake of turbulent air behind the shock wave, which alters the pressure around the wing. This in turn may cause loss of lift, and some aircraft may lose height. In others, one wing may drop. The aircraft may pitch, or porpoise as it's called, or undergo other weaving movements such as snaking and Dutch roll. The turbulent airflow from behind the shock waves may hit the tailplane or other parts of the aircraft and cause buffeting. Or the controls may be affected. Here, slowed up about 40 times, is a schlieren picture of what may happen to an aileron as a result of shock waves. How have aircraft designers overcome these shock wave troubles? One way is to put them off to still higher speeds by actually raising the critical Mach number of an aircraft. The designer does this in two ways. First, by using relatively thin wings, wing sections whose thickness is small compared with their width from front to rear. The thinner the wing, the less the air is speeded up while traveling over it, and so the higher the critical Mach number. The second method is to sweep the wing back. Suppose this unswept wing has a critical Mach number of 0.8. If we sweep the wing back, only that part of the airflow at right angles to the wing is speeded up as it passes over the wing. So the critical Mach number is raised, in this case to 0.98. High-speed airliners of today use thin wings and sweep back to obtain high critical Mach numbers. By cruising at high speeds, but still below the critical Mach number, they avoid shock waves altogether and the troubles that come with them. But wings can't be made too thin or too highly swept back, or low-speed flight and landing would suffer. And what about aircraft which have to fly much faster than sound? Designers of such aircraft have had to accept the presence of shock waves and find ways of overcoming their effects. Above the critical Mach number, speeds are grouped into two ranges. The transonic range covers speeds at which the airflow is mixed, part subsonic, part supersonic. Here, subsonic airflow is shown in dark green and supersonic in light green. Remember that wherever there are shock waves on the aircraft, there are supersonic regions in front of them. The transonic range, shown here in this wind tunnel picture, begins at the critical Mach number and extends through Mach 1, the speed of sound, to about Mach 1.3, depending on the design of the aircraft. Speeds higher than this come into the supersonic range. Here, shock waves are still present, but the airflow is now supersonic everywhere, even behind them. For transonic flight, thin wings and sweepback are again used. For, by lowering the speed of the air as it passes over the wing, they reduce the severity of the shock waves. Compare the behavior of thicker and thinner wings in the wind tunnel at the same speeds. Streamlining an aircraft's cross-section helps to reduce the huge increase in drag. The aircraft's shape is modified so that the cross-section area pushing through the air changes smoothly from nose to tail. This usually means giving the fuselage a waist to compensate for the wings and flaring it out again behind. Above Mach 1, sharp leading edges and pointed nose help to reduce the drag caused by another shock wave which appears in front, the bow wave. This is rather like a bow wave on water. With a sharp leading edge, the bow wave attaches itself, more like this one from a motorboat. Buffeting is reduced by putting the tail plane above the wings, or below them, so that it misses the turbulent air coming from the shock waves on the wings. Control of the aircraft with shock waves is also helped by an all-moving tailplane instead of the normal fixed tailplane with elevators on the end. Powered controls are also essential. Shock waves exert such huge forces on all the control surfaces that no pilot could control the aircraft manually. All these improvements in design have conquered shock wave troubles and helped to make transonic flight safe and relatively simple. In supersonic flight, the air flowing past every part of the aircraft is supersonic and behaves quite differently from subsonic airflow. Here's a section of a supersonic wing. The sudden corner on it couldn't be used on a subsonic wing, for, as the smoke shows here, subsonic airflow becomes turbulent and confused past the corner. But supersonic flow, surprisingly enough, can turn the same corner easily, as shown in this diagram. As it does so, the air expands through the region shown here in blue, and pressure is reduced. A sloping shock wave, coming from the opposite kind of corner, swings supersonic airflow smoothly the other way. The corner may be at the leading edge of a wing. So supersonic aircraft can use sharp corners, as for instance, the double wedge wing section. The changes of pressure caused by the shock wave and blue areas give the wing its lift. Here's a wind tunnel picture at nearly twice the speed of sound. Another shape, formed by two arcs of circles, is the biconvex, which, like the double wedge, has sharply pointed front and rear edges. The trouble about these wing sections is that they give very poor lift at low speeds. They can be used on missiles such as this one with double wedge wings. But for manned aircraft, which have to take off and land, it's not so simple. And very long runways are needed, and sometimes even extra braking devices. Today, the problem is met for most supersonic aircraft by once again sweeping the wings back at a bigger angle than for subsonic or transonic aircraft. The wings can then have a subsonic section, rounded leading edges, smooth curved surfaces, and no sharp corners. But there are still a few supersonic aircraft today with straight, unswept wings using the supersonic biconvex type of wing section. And at speeds around Mach 2, twice the speed of sound, opinions are still divided about straight or highly swept wings or the delta. For the future, new ideas are on the drawing board. Vertical takeoff and landing to overcome some of the low-speed difficulties. Machines which will change shape during flight from straight-winged at low speeds to highly swept at supersonic speeds. Shapes like these may one day fly passengers at speeds much faster than sound.